Okay, so where we left last class, we were going through actually a lot of the stuff that you'll need to do for the assignment. And we got sort of partway into constructing an algorithm for solving these problems, which I know Carl actually wrote down one of his own. I'm going to write down one, and we can discuss whether we have the same algorithm and what you think. But so I'll just remind you, we're talking about enzyme kinetics, and we're coming up with what to do when you have fairly complex mechanisms of enzyme kinetics and how you do the various balances that let you solve the problem. So what's the problem we're trying to solve? Why are we doing all of this stuff? What's the end goal? What's our purpose in all of the mess that I was putting on? Right, so our goal is so what we're trying to do is we're trying to come up with some sort of rate equation that's a function of measurable things. So our substrate concentration, if it's there, inhibitor concentration, the initial concentration of enzyme. And why do we want to do that? That allows us what that allows us to do is create a model that we can do experiments on. So the model tells us what the rate is in terms of a changing substrate concentration and inhibitor concentration and an initial enzyme concentration. And we can do experimental measurements that then allow us to determine what our Km or Km prime or Km double prime or Km apparent and Vm or Vm apparent are in terms of all of those measurable quantities. So ultimately what that'll let us do is design a reactor that we have a model system for with known numbers for Km and Vm. So we don't have to always run it and see how it does it so that we know that it'll work. We can run it in two conditions, or we can run little tiny experiments in two conditions and then be able to predict a range of function for a reactor system. Okay, does that make sense as our goal? Okay, so the first thing we do to do that is we determine our rate equation. So usually the rate equation is based on the very last part. So you've got your goes to product, part of the product plus enzyme, part of the equation. So we're trying to figure out what the rate of product formation is in terms of that last part of the equation. So typically, but not always, we have this rate equals K2 dx. Not always. You'll see that we sometimes have situations where we say that's actually an equilibrium, in which case you'd have minus K minus 2 P times E, or something like that. So if you're given something where it's a little bit different than you've already seen, it may not be that rate equation, but that's essentially what we're trying. That's often what the rate equation is, but just not always. Okay, so now we have a rate equation, but it's not useful because it's in terms of something we can't measure. So our next goal is to get an equation for ES with E naught S, sorry, S, I, etc. Okay, makes sense? Like, that's getting us closer to that ultimate goal. So our next step in that is to an enzyme balance. E naught equals all the different ways, all the different things, ways that the enzyme can be balanced. So it could be pure enzyme plus ES complex plus ESI, depending on what your mechanism is. The enzyme can be in a bunch of different ways. So that's a basic mass balance equation. That one you can do no matter what the assumption is. Okay, so that equation and that equation are equations you do that are just true, based on a mechanism, okay? So, but they're not enough to solve your problem for you. So the third step is use an assumption. So the steady state or rapid equilibrium to create more equations. So for the rapid equilibrium, you've got forward rate equals reverse rate for each part of the mechanism that has a forward and reverse arrow. So every time you see that, you say for each side of that, the forward rate equals the reverse rate for the rapid equilibrium approach. Okay? And for the steady state approach, you've got the change in any complex with time equals rate forward minus rate reverse equals 0. Okay, so there, instead of here, for the rapid equilibrium, we're focusing on what's happening at the arrows. For the steady state, we're focusing at what happens, how the complex is formed and lost. Does that make sense? Yeah.
So aren't they technically the same?
No.
Forward rate and reverse, they're
So-
equal, but that's
So
for
that's
just
actually rate, I should say rate or formed. So equals rate
Oh, okay. That's okay.
lost. So that's actually a more accurate way of saying it. So here, the forward rate are based around the arrows. That rate there is equal to that rate there. But this one, we're focusing on the actual complex.
Yeah.
So how fast is it made minus how fast is it lost equals 0. So you're looking at, you're centering the balance on a different thing when you have your steady state versus your rapid equilibrium assumptions. That makes sense to everybody? Any questions? Okay, and then the next depends on sort of what your actual equations are, how you solve it. Everyone will have a slightly different way of solving it. But sort of the basic method, sub your balance into your, say, your first equation I'm gonna call it 3A, to find an equation, find the expression for, say, enzyme concentration, then sub into 3B for your complex formation. And then step 5, sub 4 into your rate equation.
We only use one sometimes, right, for each formula?
Right, so you must choose.
So what is 3A are you referring to?
So usually there's usually gonna be more than one equilibrium component. I mean, there's not in the basic Michaelis-Menten equation, but then you don't have any extra expressions, so you only need one. So in that case, you wouldn't have, just to derive Michaelis-Menten, you don't need that part.
Okay.
But if you have a more complex mechanism, then you may have 3A and 3B and 3C, depending on what the mechanism is. Does that make sense to everybody? Okay, so it's not necessarily like super straightforward to actually do the math part. Yeah.
So 1 and 2 are basically the same equation, right? So you can write out,
What do you mean they're the same equation?
so aren't you rearranging in order to find G naught? You're rearranging your equation that you get for ES?
No, so equation 1 is just our basic rate
No,
equation.
yeah, sorry,
Sorry.
I meant the goal.
Goal 1 and
Never
goal
mind,
2?
it's not part of 1, so it's,
Right, so goal 2 essentially gets you to goal 1. So goal 2 recognizes that your rate equation, you've got your rate equation here. So in order to figure out what rate is in terms of S and I and E naught, you have to figure out what ES is in terms of S and I and E naught. Does that make sense?
and then you rearrange that in order to find E naught
So
to do 2?
here, you mean?
Yeah.
No, so then we end up working backwards. Okay, so these are our goals. So in order to figure out what rate is in terms of those things, we need to figure out what rate is in terms of, usually the rate is in terms of ES. Depending on your mechanism, this may be a more complicated rate, but mostly it's this rate. So if it's this rate, then the next step is the next goal is pretty straightforward, which is just to get some expression for ES that's in terms of all those things that will allow you to solve this goal. So it's pretty easy. Then the one thing, the reason I emphasized it as different steps is twofold. One, that it's not always that simple an equation, and two, it's not unknown that people will just, when I give an exam question, they'll just figure out what the equation is in terms of ES, but they won't go that extra step to put the K2 in to give me what the rate equation actually is. That makes sense, Ava? Sorry.
Yeah, so, yeah.
Okay.
Okay, when we were talking the other day,
Yep.
so we're going back to the rapid equilibrium, one of the things that you said, I wrote down a set of equations for Km and Ki from the reaction cycle diagram, so the balance around those, and it starts substituting those back out to the equations until you find P. So can you explain that?
So, what Carl's referring to in the rapid equilibrium equation is that I say here, what we're doing is saying forward rate equals reverse rate. So in this case, usually there's like something like a K1 and K minus 1, or Ki and K minus I, the little k's that are rate constants moving forward in reverse reactions. So there, we're going to basically take those and say K minus 1 over K1 equals,
The same thing, the one.
they're never going to be, no. So we talked about this last class as well. The rates, K minus 1 times the concentration of E times substrate
Yeah.
equals K minus, or K1 times ES. But K1 and K minus 1 are not the same thing. So your rate constants aren't the same, your rates are the same.
Okay. Okay. And then that's considered.
Equals KM or KM, well, I guess it's actually KM prime. And that's equals KM. Or if it's KI or K minus I and KI, then it'll equal KI. Big KI.
And you have to tell us how every equilibrium is in the reaction.
Yeah, if you say, so what Carl just asked is if it's a complex mechanism that has a lot of equilibrium back and forth arrows, when you make the rapid equilibrium assumption, you have to do this over every back and forth arrow. So if you have 3 back and forth arrows in your mechanism, then you get 3 equations out of doing this rapid equilibrium assumption. Similarly, for steady state, if you have 2 different enzyme complexes, say one that includes the inhibitor, then you have to do you get 2 equations out of this because you have the 2 different enzyme inhibitor or the complexes that involve the enzyme. Does that make sense? So let's go back. We never quite finished the uncompetitive inhibition. So we'll go back and do that example. Oh, shoot. I didn't bring my whole. It's okay, I remember it. So if you remember, we had E plus S goes to enzyme substrate complex, goes to enzyme plus product, and then here we had, plus I goes to enzyme substrate inhibitor complex. Okay, so that was I'll write it down. Uncompetitive inhibition. So we had competitive inhibition where the inhibitor could alternately bind in the active site of the enzyme instead of the substrate. We had non-competitive inhibition where it bound somewhere else on the enzyme and changed the affinity of the enzyme for the substrate. And then the uncompetitive inhibition is where the enzyme and the substrate come together and the inhibitor binds to both of them and interferes with it coming off as product. Okay, so and the way we showed that was this mechanism. Okay, so the way that the book gets to the final answer is using the rapid equilibrium approach. So rather than me writing out the rapid equilibrium approach, I want you to, again, try and get experience doing that. So I'll give you 5 minutes or so. I'll walk around and everyone try and write out over each. Remember, you're going to have a balance over this part, just that part, that the forward equals the reverse, and then you're going to have a balance over just this part, that the forward equals the reverse. Right, so I'll write that up. So let's do K1, K minus 1, Ki, K minus I, and let's define big Km prime equals K minus 1 over K1 and big Ki equals K minus I over little k I. And so essentially what I want you to do in doing your equations for rapid equilibrium is come up with an expression for Ki and Km prime in terms of the concentrations of complexes and enzyme and so on. Yeah, but you need to know how to do the same setups. So, yeah, Emily just pointed out that in fact I gave you the solutions at the end, sort of mid to the end of last class. So if you're on the ball, you can go back and check your work and see if it matches what I gave you last class. But I still want you to be able to work it out so that you get there yourselves. Every back and forth there.
Oh, okay.
Back and forth
Oh.
there. So that's the deal with the rapid equilibrium is every time you have a back and forth equilibrium arrow, that's going to give you an equation.
Okay.
And then if we were doing steady state, every time there's a different complex there and there, that would give you an equation.
So like for that one, K1 times concentration of S is equal to K1 times concentration.
Yep.
That's right. Okay.
Yep.
Oh.
Does that make sense? Yeah, so don't try and do too many steps all at once. Step by step. No, but I think you can. Still just, yes, because that's or I suppose if you're doing really fast, less than
It was up
adrenaline.
Okay.
until 10:30, probably 10:40, it got knocked out. I'm actually walking down the area, I didn't go to it until out, it was to see the final position. And then it was something we got really good. Can I see that photo? That's really cool. Yeah. Would that be sending then? No. Yeah, you would. Yeah. And then you can make that longer. Oh, okay. So, yeah.
So you just fix
Make
this
it
stuff.
longer and then you get the red from that.
Okay, just so that you're confident in how you get there and
Yeah.
yeah, because it's easy to.
So
Just
there's a
wanna
bunch of-
make sure that you're on it.
Oh, that's so reply.
Yeah, because that times that equals that times that.
Yeah.
So you can't have this if you're not doing a rapid equilibrium assumption.
So, E0 is equal to some original
Yep.
concentration is equal to.
Yep.
And then I assume the main enzyme is generated or lost.
Oh, so you're even actually going a huge step ahead of where you want to go. We're just use the definitions of the and just get those equations. We're good for now.
Oh, okay.
But you're right, the next step would be to sub in, remembering the algorithm, the next step would be to sub in to get next, to put it in terms of E, like you want to go in terms of E, so your enzyme concentration equals something by using the enzyme balance.
Yeah, so
And
you're
then-
getting the enzyme balance for ES.
Yeah.
So you wouldn't tend to use it for ES, because ES is actually what we're trying to get to.
Right,
So
okay.
your next step along the way is to do the E, and then in your second equation, you'll find your expression for E. You'll sub your expression for E into the second equation, and that will sub balance in terms of ES,
Yeah,
because you're
plugging
plugging
backwards.
into the right equation.
Reverse is ES K minus one, right? Now, K and time is in the form of K minus one. Take this, K minus one divided by K1.
Yeah, so that would be your next step, now that you've got your two equations there. Then you're gonna use this, and maybe for this one, use this equation to get the expressions in terms of
Yes, you can do that.
and then you can sub that back into, say,
That's all I can
working for agriculture use that, like microbiology students.
say. But essentially you're gonna, you don't try and get an expression for ES right away because then it's your final goal.
So like I
Yeah.
Okay, so
yeah, it's pretty
you're missing some.
It's actually really awesome.
Yeah, okay. So you're sort of skipping some steps, but you got your on the right track, so you're basically already close to and then you're assuming that and your next step is find an expression for E and then you're not trying to solve right away for the ES, you're trying to maybe solve in terms of ESI and then you get in terms of Yeah, so what you actually end up doing is so I'm always so just to I think everyone has figured out how to do just those equations. So let's go through it again. The next step usually is to rearrange your enzyme balance, say, so that the enzyme balance is E equals E naught minus ES minus ESI. And then you have that expression for E that has now an ESI and an ES in it. And you would put it into one of your rapid equilibrium expressions. So let's just see what we've got. We've got AM prime equals E times S over ES, which is I think what everybody had. So what you do there is you have your rearranged enzyme balance that gives you an expression for E that's in terms of everything else. So you can put that in there.
Wait,
So
can you do that stuff?
So, okay, let's go through it a little bit more slowly. We've got now, let's rearrange it. We've got this, and we've got E, our enzyme balance equals E naught minus ES minus ESI, right? So then you rearrange that in terms of, basically, your goal is to have the very last thing you do be an expression in terms of ES. So you never want to have your first step be putting everything in terms of ES, because that's your goal at the end. You want to just be left with ES because that's what you're going to put into your rate equation at the end. So your first and easiest step is to put an E into it, and then your next easiest step is to have an expression in terms of ESI, and then you can solve for ES. Everyone get where I'm going with that? Okay, so then you would put that into there. What you'd end up with is an expression that now has E naught, ES, and ESI. And
Times S over ES.
yeah, so you'd have an S, but you get rid of that E. You have an S, and you're introducing now this ESI, and you'd still have the ES.
S times that.
Times
Like,
all of
like,
that.
Can you expand that out? Does enzymes expand like?
Yeah, it's just like math. It is math. It is math. So then, like, you can rearrange that expression so that it's in terms of ESI, right? So then you have an expression for ESI equals something that is in terms of ES and E naught and S, right? Everyone follow where I'm going with this? And then you'd sub that whole thing, so E, S, I equals a function of E naught, S, and ES. And you sub that into your other equation, which is KI equals ES times I over ESI. Okay, so you've got this ESI term that is now just in terms of E naught, S, and ES. You sub that into the bottom there, and then you now have something that's just in terms of ES, I, and presumably E naught, S, and ES. Well, now you know everything except for the ES, so you can do a lot of rearranging to get an expression that now ends up being ES equals something that you know. And then you sub that into rate equals K2 times ES, and that's in terms of everything that you know. So everyone follow that process that I'm taking? CC?
Will we get a chance to practice steady state assumption in class sometime before the midterm?
Sure. Sure, we can do that. So the other thing I'm going to say is that for midterms, I'm not going to ask you to solve the really long, ugly math, because that takes time and it's not really what I'm testing you on.
Okay.
Like, I trust that you're all able to do rearranging and solve long, ugly math. You'll have to do it in your assignment, but you won't have to do it in an exam situation, because that's not an efficient use of exam time in testing what I've actually taught you. Because I'm not actually teaching you how to do math. I'm trusting you that you know how to do math. Okay.
What's the final answer?
So the final answer, which I'm not going to go through all the long, ugly math for, is actually pretty ugly. Well, it all depends on how you rearrange it.
So like,
right?
yeah, how do you do that? Because like that's, I'm sure the assignment, and like the book jumps from that to that. It's like, what the hell?
So,
Like,
so some of it is that the book is trying to get everything to look like Michaelis Menten kinetics. So if you do lots of rearranging, then you too can get your long, ugly expression that looks somewhat different than that to rearrange to something that looks like Michaelis Menten kinetics. So that's always the book's goal, is to make it look like Michaelis Menten kinetics with something a little bit different.
and that's great if your problem is exactly what the book had, but like you get to the first question,
So-
it's a different setup. And you're
And
like,
that's,
what the hell did this guy, like, how do I don't get how to shift this?
so.
How do you make this when it's not exactly what the book has?
So, in some cases, if you're not given what it should look like in the final situation, you may come up with different expressions. And that's fine, because as long as you've done everything correctly along the way, you're fine, because they'll end up being equivalent, just not rearranged the same way. If it tells you it wants it to look like something final, then you're gonna have to play with rearranging a bit until you get it to look the same way. Ava?
Where did the E naught go?
So remember, B max equals K2 E naught. So that's the definition we've used several times, is that our B max is just K2 times E naught, because when you have infinite substrate concentration, ES equals E naught.
Okay, I forgot.
Yeah. Yeah. So it's just reminding yourself of some of those definitions as you go along. But that's a really good question. Okay, so the other thing we have call this EM apparent, and this KM apparent. Now we can rearrange it so it's rate equals VM apparent times S over K prime M apparent plus S. So again, what it's telling you is that if you have lots of inhibitor, you're going to get to, in this case, for uncompetitive inhibition, you're going to get to, so we've got rate, substrate concentration against rate. So there's your normal. You're not going to get to, in this case with this inhibitor that binds to the enzyme and the complex, you're not going to get to as high a final concentration, and you're going to have a higher Km, so it's basically going to seem like it has a different affinity. So your half Vmax happens at a different substrate concentration as well. So if we look back, at our Lineweaver-Burke plot, essentially a parallel line. So both your, basically your affinity between the enzyme and the substrate looks different. That's your Km. So now you're apparently, if you do experimental measurements, it's going to look like you've got a different one, and your Vmax is going to be different.
Will they always be parallel? Because like
Not necessarily.
Yeah.
Yeah, not necessarily. That's a good question. But you are likely to have both of those values be different.
But I mean, if they're not
Yeah.
changing at the same rate, but
Yeah. Yeah. Okay.
How do we simplify this on a test? Do we have to simplify it in terms of exactly that to get into KM apparent and K?
So that's exactly what I was saying, is on a test, what I'm gonna ask you to do is set up those initial expressions so that you have every equation that you would need that would allow you to solve it. Then I basically ask you to write out the algorithm. I'd say, what are the steps that you would then take in order to solve it without actually solving it?
Oh, okay,
Yeah, in a test situation,
Yeah.
not an assignment.
yeah.
Okay, still, the step getting from down there to up there, I don't understand that. Because like, over there, you have a bunch of arrows, you can actually substitute everything in. And then up
So-
here, you have totally different things, and I can't draw the connection between them.
Okay, so I didn't go through the math.
Yeah, and I don't want you to, that's
And
fine.
it would take forever for me to actually go
So
through the
like,
math.
that's just a rearrangement of that, is that what you mean?
Yes,
Okay, all right, that is, okay.
yes. So Carl's question is it even possible to get from what I said was your final substitution to up there? And what I'll say again is we had a rate expression where rate equaled K2 times E naught. Okay, so here our Vmax is K2 times E naught. So that's what that's telling you, is that you've got your K2 up here, and then somehow your balance for ES has an E naught, this one has an I, has an S, has your KI, has your KM, I, KI, and So we know from the steps that we took that we should already have an expression for ES that only has those values in it. E naught from this part and S, I, K, I, or S, S, I, E naught, and then our KIs and KMs. More or less?
Alright, yeah, and then also down there, I see how you're putting the E into the E on the numerator of K prime M. But then,
Am I wiped out?
no, it's okay, you can still read it, and then.
Down here? Yes.
No, sorry, the
Oh,
other stuff,
sorry.
okay, I understand the
Oh,
left
here,
side.
here, yes. So.
And then you're saying
A lot
ES
of-
on.
a bit of as well. So use your enzyme balance
Yeah, so you
in
put
terms
those
of
three
E,
terms.
so that now you have something that just is in terms
Yeah.
of
E naught,
ES and
ES.
PI, or
Yeah.
ESI.
Yeah, E naught, E up S, ESI.
Yeah.
And then you say we still know ESI, so
So
then.
we rearrange this so that it's in terms of ESI.
Okay, well, this is what you did on the other side, is you wrote in terms of expression of ESI.
Yeah,
You
so-
just wrote it as a function of ES.
So all we're doing is after we set that in, this whole expression just has ES, E naught, ESI, and S.
Yeah,
So you rearrange this one so that it's in terms of ESI.
okay.
So it's a function now, you have ESI as a function of E naught, S, ES, and ESI. Or sorry,
Yeah, I know what you mean, yeah. Right.
and then, because you now have this ESI that's in terms of everything
What
else.
is that
but it's-
definition? You didn't put function there, you didn't like,
I didn't do the math.
how would you get that?
Oh, do you want me to?
Is that the same as getting?
So here, where do we go? We have, I'll write it out again just for a second.
No, it's okay, this.
S over ES. Okay, so now what we have is, instead of we substitute for that E, we've got
E naught,
E naught,
minus ES, minus ESI.
S minus ESI, brackets.
Yeah.
So what you'd then do is you'd say Km prime ES, okay, on that,
Yeah.
equals,
No, minus.
or sorry, prime S divided by, let's say divided by S,
Okay.
okay, equals E naught minus ES minus ESI.
Yeah.
Okay, and then all you do is, you've got ESI, so your ESI over this side now equals E naught minus ES minus KMES over S.
Yeah.
So you take that whole expression and sub it into KIES I divided by that expression.
So you're gonna end up with KI, obviously.
Yeah.
KI, so.
Yeah.
So you rearrange that KI to ES,
It's so that it's all in terms of ES.
ESI.
No. Okay. So Carl's trying to go through the actual steps that you take. So I know some of you are cool with that, so just keep it down so that.
We can do that after.
So, well, we've only got a couple minutes left, so we'll just finish this. And I'm sure there are a couple of people who still want to go through it a little bit more carefully. So again, the steps were, you had your Km prime, and you put in your enzyme balance in terms of E into your Km prime value. So now what you got was an expression that you could rearrange so that you have an expression for ESI that's in terms of ES, E naught, S, and Km prime. Okay, so now we've got something that's ESI, and what we had here was KI equals ES times I over ESI. And so now we can basically sub in, what did we say it was? E naught minus ES minus KM prime ES that's got Ki, Es, I, Es again, E naught, Es, and S. Okay, so now we've got all the tools that we need to just put everything in terms of ES. Okay, so rearranging this so that you isolate the ES is not an easy, pretty straightforward thing to do.
Why don't you just leave it in the E now, I think, level up form, and just make sure there's an ES on all terms, bring the ES out, and just solve that.
Because then what you end up with is something that's like ESI equals all that stuff.
Well, I did, right?
And the whole idea is that you,
KI equals stuff.
yeah, so your whole end goal is you're trying to get rate equals K2 times ES. So you want to get an expression
For EI.
for ES at the end of the day. So you don't want to rush too quickly to have an expression for ES, because what you end up with then is an expression for like E or an expression for ESI at the end of the day, which is not useful in terms of your rate equation. Because your rate equation, you've just got the ES. So this, again, it's not pretty math, but you know, you multiply both sides by the denominator, and then you factor out the ES from everything. So you have ES times blah 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 equals something else, and then you divide everything both sides by the whatever ES is multiplied by, and you've got an expression ES equals some big ugly math. Does that make sense? How many people are lost in what I'm explaining? No? Anyone? Everyone understand? Okay, so what we'll do next class is we'll develop an expression for what happens when we have substrate inhibition. But what I'll set up the rapid equilibrium expressions and tell you what the thing is at the end of the day, but what our in-class practice will be trying the steady state approach for doing the equation setup. Okay, so we'll do that at 5:30.